Hello everyone, welcome back to Bytes of CC. So in this lecture, we will be learning about the attention mechanism in artificial neural network. Now, before we delve into how artificial neural network uses attention mechanism, let us try and understand this from a human-centric point of view. Say you have enrolled for a data science course and now you enter into your classroom and you sit beside your friend who has something very interesting to tell you about the previous day's match. Next, there is a window on the other side, and something very interesting is going on outside the window. And then your professor comes in and he starts teaching you LSTM. Now, if you have to listen to your professor and also to the conversation of your friend and also look outside the window, you will probably end up doing nothing. So, you will have to focus on any one of them. So, how will you choose? Now, see, you were here because you were very interested in learning about natural language processing. So, anything that you like to do or you have some intention, that is known as the volitional cue. And in artificial neural network, volitional cue is known as the query. And any object that fetches attention in the environment is known as the non-volitional cue, and that inattention mechanism is known as key. So, what are the non volitional cues in this environment that I'm talking about? Um, so, we have three actually objects we have talked about so far, which is fetching you attention. One is your friend, another one is the window, and the third person is your professor. Now, every key comes with an associated value. So let us know that which key has which value in this context. So your key friend has the value of interesting conversation. And the key outside the window has the value of nice view. And your professor has the value of LSTM lecture. Something that is he is offering. So now the volitional cue will interact with all the non-volitional cue or the keys in the environment, and it will assign a weight to the value that the key is offering. Now your volitional cue in this case is to learn about NLP. Now you associate this query with this key friend. Now, whereas your friend has something very interesting to tell you, it has got nothing to do with NLP. So you assign a weight of say 0.5 to that. Then you associate this query with the key outside the window. So outside the window is offering you something interesting, some nice view or anything, something like that. But that is again far it is very much distant from your query, which is NLP. So you associate a value of say 0.3 to that. Now you look at your professor and he's teaching you LSTM, which is very essential if you like to learn about NLP. So you attach a value of 0.9 to this value LSTM lecture. And ultimately you place your attention on your professor. So now this is known as attention pooling. Now what is attention pooling? Attention pooling is like you attach weight to the key and then you sum that up. Like it is the interaction between the queries and keys which selectively aggregate values to produce the output. So say you have a query which is denoted as X and you have n key value pairs, like these are denoted as x1 y1. So x stands for the key and this stands for the value. So the first very important work which was done in attention pooling was by Nadara and Watson, which is known as the Nadara-Watson kernel regression, and they suggested the equation of the attention pooling function, which says that this is the summation of the weight and the value. So basically this is the weight part which I was talking about. This talks about the interaction between the query and the key. So what does this mean? In the numerator, this K stands for kernel. So kernel is, well, it is, you can call it a set of function. a special function. I'll be using a kernel to actually show you how this works. So this actually computes the kernel of the distance between the query and the key, a particular key, and in the denominator you will take the summation of this, that is the kernel of the query with all the keys. So this provides the weight that I was talking about in the introduction. So now let us take a particular kernel. We are taking the Gaussian kernel, which the equation looks like this. So ku equals to 1 by root over 2 pi exponential of minus u square by 2. So in your case, the u is x minus xi. This is your u. So if I place if I replace this kernel with this Gaussian kernel, the equation looks like this. Now if you're wondering where is this 1 by root over 2 pi factor, so let me show you where it has gone. So your numerator should have this 1 by root over 2 pi here. And if you consider the denominator, like if you expand this summation term here, so there was a summation here, if you expand this, if you place this here, it is supposed to look like 1 by root over 2 pi e to the power x minus, so your xj starts from 1, so x1 whole square to the power 2. The second term would be again plus 1 by root over 2 pi e to the power minus, oh there should be a minus over here, sorry, minus x minus x2 whole square divided by 2, and so on. So you can actually take this 1 by root over 2 pi. Let me show you here. You are taking actually this 1 by root over 2 pi outside the summation, and now this and this gets cancelled out, and this is what you're getting, like exponential minus half x minus xj whole square. So now if you consider, if you just replace this entire minus half x minus xi whole square as say zi, and you replace this as zj, this term will look roughly like this: e to the power zi divided by sum over from j equals to 1 to k, e to the power zj. So we are considering k, you can also replace this with n. This is basically a variable, so you can denote it as n, m, whatever. So this looks like this. So now, what is this? This is actually the Softmax activation function that we use for multinomial probability distribution. And now if you replace this part, like if you use this Softmax, we can say that this attention pulling function is now the sum over I equals to 1 to n softmax of zj, which is minus half x minus xi whole square into yi. So now your weight function looks like this. This is your weight function. So why are we actually doing this? We are doing it because see, we are actually trying to build this attention pulling function using whatever we already have in the artificial neural network. So softmax function is something we already are dealing with. So naturally we are converting this into this. And now if you look into this factor, now this is actually known as the non-parametric attention pooling. Why? Because see, there is no learnable factor like weight or bias, which are known as the learnable parameters. These are not attached to this particular equation, so we will call it non-parametric attention pooling. Now, in order for these type of functions to converge, it takes a lot of examples, and sometimes we don't have so many examples to actually converge the equation. So we are going to shift to the parametric attention pooling, which is again suggested by Nadaraya and Watson. So now what we do is, this was the original attention pooling function. Now to this attention pooling function, if you consider the Gaussian kernel again, we are multiplying this W to x minus xi and x minus xj at the same time. So what we are doing here is, we are actually passing this x minus xi through a fully connected layer. Now, if you remember the MLP lecture, as we said that the output of an input, if you pass an input x through a fully connected layer, the output will be equals to wx plus b. So now this b is your bias and w is the learnable weight. Now what are we doing here is, we are setting this b to 0, or we can say we are setting b to false. So naturally, if you pass this x, in our case x minus xi, if you pass this through a fully connected layer, you will get what we call it a linearly transformed x minus xi, because whenever it attaches a weight to it, we call it a linear transformation. So now if you look into this again, if you consider this as zj and zi, sorry, and this as zj, we can again find the softmax. If you just consider this part, don't consider yi or don't consider this part, this exponential part again looks like this. So obviously we'll be using the softmax over here. And now if you look into this part, minus half x minus xi into w whole square. So if you look at this part only, you can call it as a function of x and xi. So why are we not considering w? Because w is something that we are adding in order to make this learnable. We are actually making it pass through a fully connected layer. So we are not considering w here. The constraints that we are considering are, the factors that we are considering are x and xi. So we can rewrite this as like a function a of x and xi. Now we have a special name for this function a, and we call it attention scoring function. Now in the now if you rewrite this equation again, consider this equation, and we rewrite the equation. So we can rewrite the attention pooling function as a summation from I equals to 1 to n, and if we consider this part, we call it as alpha xxi into yi. Now this, what is this alpha function? If you consider this softmax, like if you consider this shape, this alpha is basically softmax of your attention scoring function. So from now on, whenever we are trying to compute attention pooling function, this will be the basis. So it will be the softmax of the attention scoring function, and that will be multiplied with yi, and a summation will be done over that. So this is what is given in this particular, whatever I said, that alpha q ki, q is the query and ki is the key, is the softmax of the attention pooling attention scoring function of q query and key, which is again, if I replace this softmax to the original softmax equation, this is your zi or whatever you call it. So it will be exponential of attention scoring function of query and key divided by a summation from j from 1 to m of exponential of attention scoring function of all the queries and the keys. Now let us move into the attention scoring function. Let us learn some important attention scoring functions. So the first attention scoring function that we'll be learning is the additive attention. So now queries and keys can be of same vector dimension or different vector dimensions in this case. And the equation looks like this. The attention scoring function of query and key is supposed to look like we are actually doing a linear transformation of query and key with this weights wq and wk, and then we take a hyperbolic tan over this, and then again we multiply that to the transpose of this another weight weight matrix. This is wv. So your WQ, say we are considering that your query has a dimension of Q and the key has a dimension of K. So WQ will be a matrix of dimension H cross Q, where H is the hidden layer, and WK naturally will be of dimension H cross K. And when you multiply WQ with Q, it will be giving you, the resultant will be of dimension H, and this resultant will also be of dimension H, and naturally your WV has also the dimension of WV also has to be of H. Now in practice, what we do, how do we actually compute this additive attention? So what we do is we take the raw query, we pass it through a fully connected layer. Like this is fully connected layer. Now this is not really this is how fully connected layer is actually depicted. I am using this convention. And then you take the raw key and again you pass it through a fully connected layer and you get the linearly transformed key. Now you concatenate this query and key, and then you make it pass through another fully connected layer, and then you take the tanh activation function on the resultant. This is how it is actually implemented in practice. Now this is a little bit computationally what shall I say, a little bit extensive. So we will be moving on to a lighter version of it, which is known as the scale dot product attention. But the problem is, if you want to implement scale dot product attention, both the queries and keys have to have the same vector dimension. And we also have to consider, consider that all the elements of queries and the keys are independent and they have a zero mean and a variance D. And let us compute the attention for n queries with m key value pairs, and we consider that the query is of dimension n cross D, that is the vector dimension of query is D, and we have the key which is of dimension m cross D, and the values which have a dimension of m cross V. Now the values can have a different vector dimension than the query and the key. That won't be a problem. And your attention scoring, the attention pooling function will look like this. We'll have to take a summation, of course. So this will look like this. And this is your attention scoring function, which is the scale dot product attention. So what we are doing is we will be actually linearly translating the query. So here also we will be like passing this query and the key through a fully connected layer individually, and we will be doing a multiplication of query and we'll take the transpose of key in order for it to be multipliable, and we will be dividing it with the square root of D. So why are we actually dividing this? Because we like to keep the variance unchanged. And so this is basically your scale dot product attention. Now we will be moving on to another very interesting implementation of attention, which is known as multi-head attention. So what we have done so far is we have taken the queries, keys, values, we have actually made it pass through a fully connected layer. Then we have implemented an attention scoring function which might be additive attention or scale dot product, and then we have passed it through the Softmax, and that gave us the attention pooling function. And then we multiply that with V and so on. So now, instead of just taking one set of that, we are taking multiple sets of queries, keys and values. So the queries, keys and values will be same. So what will differ is the weights we will be using. So the weight used in this query, key and value will be different from the weight of this fully connected layers. So the weights will be independent. So naturally, after linear transformation, we get k sets of queries, keys and values, and that will be passed through an attention pooling function, and the resultant from all the sets will be concatenated, and that will again be passed through a fully connected layer to get the final output. So now say we have a query which has a dimension of dq, and that will be passed over through a fully connected layer which has a weight of dimension pq cross dq. Pq again is the hidden dimension, as I mentioned earlier. If you are finding it a little difficult, I would recommend you to go through my MLP lecture so you can understand what is actually going on with WQ, the dimensions and so on. And then we consider the query of dimension dk, and that will be passed through the fully connected layer which the weights will have the dimension pk cross dk, and the values we are considering has a dimension of dv, and that will be linearly translated with the weights of dimension pv cross dv. And then each attention scoring function or each attention pulling function is hi, and that is basically the attention pulling function that is made to work over wi into q, wiq into q, wik into k, and wiv into v. And these are actually made to concatenate together, and that will be again multiplied with another weight in this fully connected layer, and this will have a dimension of p0, which is the hidden dimension, into h cross pv. Now why h cross pv? It is considered h cross pv because the ultimate we are actually there are h attention sets that we are considering, and each is known as a head. Each set is called a head, and we have got h heads. So after concatenation, this will be of dimension h into pv. So this is the number of heads multiplied with the output dimension. So since the value here is of dimension dv, and so pv into dv will give you ultimately a value like a value of dimension pv. So we have h such pvs, and from there you get h into pv. So this is your final multi-head attention. So your WO is multiplied with this, which is of dimension H into PV, where PV is the output dimension of each HI. Now, when all the queries, keys and values are the same, and we apply a multi-head attention on that, what we get is a self-attention. So self-attention is very important in a sense that actually self-attention is used as a replacement of RNN in artificial neural network. What happens here? So here x1 to xn, these are, now we are considering these as the tokens, and when a self-attention when they pass through a multi-head attention using like scale dot product, you get this output yi to yn, which is of same dimension of x1 to xn, but they are like transformed. So each head, in this case yi is the we consider this each yi is the attention, the self attention, where xi is the query and xi will be um, made to interact with all the other tokens here, and we are taking it like x1 is taken twice because this will serve as a key and this will serve as a corresponding value, and this is how the self attention is actually implemented. So here what happens is, now in RNN, what happens is RNN processes the sequences sequentially. Like if you are given a token x1, x2, x3, x4, and x5, it will sequentially, like it will first process x1, then x2, then x3, then x4, and finally x5. So if somebody asks you a question like what is the probability of generating this token x3 given that the sequence starts with the token x1, so there is no direct answer to it because the generation of this token x3 is dependent on the generation of this token x2, which is again dependent on the generation of this token x1. So there is an indirect relation between x1 and x3 but no direct relation. But in self attention, this long distance relations can also be calculated because we are considering this this function. If you consider this function, we are actually computing, if you take this x1 as the query, it will, and the other like x2, x3, x4, x5, these are the keys. So naturally it is computing the relation between x1 and x3 independently. So naturally you can find out this long distance relation, like the direct relationship between x1 and x5. What is the probability of generating this token x5? It's if the sequence starts with this token x1. So here what we will be doing, an extra step needs to be taken. If you consider using self attention in place of RNN, what we have to do is we will have to add a positional encoding, because otherwise we will not know that exactly where this x5 is placed. So when we are actually computing this attention, we don't know like where this x4, like x4 is at this position 4. So we just can't there is no positional, there is no sequential information stored in case of attention, as we have seen, we have gone through the equation, we have seen that. So what we have to do is we will have to attach a positional encoding just so that we know that what is this position or what is this position, to differentiate between the positions of the tokens. And if we can do that, this will bypass RNN, because RNN is slower and self attention is also faster than RNN. And again, the long-term dependency, which is in RNN, you cannot just consider the long-term dependencies between the tokens, which is very much needed, especially when you are processing those long sequences. So you can actually gauge those important tokens out of those long-term sequences, or a long sequence. So now this self-attention is used to build the transformer model. Now, if you want to know that how a transformer model is actually built in practice and how transformer models are implemented, so I have a medium tutorial on how to use a transformer model for summarization of a text using PyTorch. So I will be leaving the link in the description box so you can go through it and let me know how did you find that. So that's all for today. Thank you for watching.